Hey everyone, welcome to College Algebra. In this lecture video, let's talk about how to identify whether a relation is a function. So let's begin with the definition of the word relation. So a relation is simply a set of ordered pairs. The set consisting of the first components of each ordered pair is called the domain, and the set consisting of the second components of each ordered pair is called the range. So let's scroll down a little bit. So here, all right, I got input, output, first component, second component. And so I got part A, part B, part C right here of pictures. Okay, so the first component, okay, is called the domain. Second component, basically, the second component to the right is called the range. All right, so that's kind of vague what the definition is saying. So what I want you to kind of understand for right now is a relation is referring to a set of ordered pairs. A set of ordered pair has two components. Okay, the first component is normally the x values, which is our domain, and the second component, which is the y values, which is our range. All right, so the next wording here is called the word function, and this is what we're going to talk about in college algebra. Is about function. A function is a correspondence between the domain and the range, such that every element in the domain corresponds to exactly one element in the range. So again, keep on saying the word domain and range. All right. So far, we only know domain is the first component, range is the second component. So let me kind of define this a little bit better. So the word domain, okay, domain is referring to domain will always be labeled as x values. Sometimes we call them input values. All right. An input, also, we can also define it as independent variable. Okay. So when we are looking at the domain, okay, in terms of a graph, it's referring to how wide the graph is. All right. Range, we normally label as y value. Okay. It's actually considered as an output value. Sorry, this is a little mistake right here. This is an output value. So input x, output the y value. That's what it is. That's why I put the wording side by side. It's a dependent variable. Okay, range is a dependent variable. The y values is also dependent variables because the y value depends on what the x is. Okay, that's why x is considered as independent. And when we're looking at in the graphing perspective, range is referring to how tall the graph is. So let me kind of draw you a couple pictures here. Maybe it will help you understand a little bit better. So let's say I have a straight line. A linear equation is a straight line. We draw the straight line from left to the right. So a straight line has infinite number of points on them. Okay, we're just not going to write down all those points. So I need you to think in terms of two dimensions. As I draw this line from left to the right, this arrow is pointing up, but it's also pointing to the right at the same time. So two dimension. X is left and right. Y-axis is up and down, or down and up in our case. So this arrow, as you draw it, is keep on going right and going up at the same time. The other arrow, okay, is actually keep on going down and left. So what does this have to do with x and y value? Well, since I have an infinite number of x value and y value, okay, or infinite number of points on the straight line, if I keep on going, okay, I will actually keep on going very, very, very right and keep on going up, up, up. The other end, I actually is coming from, because I'm drawing from left to right, is coming from very, very left and very, very down. So in terms of left to the right, okay, or we say that's domain, how wide is this function? The width of this function got to be coming from negative infinity to positive infinity. How wide is a straight line? Well, it's infinitely wide. So when I write my interval notation, we always got to write them from small to large. So for the range, okay, this arrow keep on going down, down, down as well as going left. This arrow is keep on going up, up, up as well as going to the right. So in terms of range, which is thinking about the y value or how tall this graph is, we will look at it as from down. Let me see where that word. We will think about as down and up. How down do I coming from? Coming from negative infinity. How tall would this line go up to? Or go all the way up to in positive infinity. So we're describing our domain and range using interval notation. Okay, so let me rethink about re-saying this definition of a function. A function is a correspondence between the domain, or we can think about as x values. It's a correspondence between the x values and the y value such that every element in the domain, okay, every element in the, or every x value correspond to exactly one y value. All right, a function is a correspondence between the x values and the y values such that every x value corresponds to exactly one y value. Okay, that's what's defined as a function. So a relation, okay, can become a function. A relation is simply referring to as a set of ordered pairs. Now, this straight line here is actually going to be a function, okay, but this is in terms of a graph. So we will talk about both of these. Talk about a relation being a function in terms of ordered pairs, okay. Talk about function as in terms of as a graphing form or equation form. So here, the example on the graph I have here, A, B, and C is trying to attempt to show you whether the relation is a function, not a function. So I'm going to just do this, okay? I'm going to look at this part A here and say, see that P to M? So P is an input, which is your X value, right? Input is domain over X value. It's different way of saying the same thing. So that's P comma M. Normally I would say X and Y, but I'm specifically saying what using P and N. Q and N, R and N. Okay, first component, second component. Okay, to be a function, every X value corresponds to exactly one value. That's why this is actually a function. This three order pair together is called a relation. Together is called a relation, and this relation is a function. All right, this relation P to X, Q to Y, R to Z is this relation. This three order pair together is also these three order pair together is called a function. And this three order pair together is called a relation, and this relation is actually considered as a function. So what is not to be a function? Okay, so we got to think about this a little bit backwards. Every X value corresponds to exactly one Y value. All right, so we basically cannot have. Let me write the relation here. P correspond with X. Q is to Y. Q is to Z. So think about this. Every X corresponds to exactly one Y. So this is actually one X correspond to this Y. This is another X this is the same X, but correspond to a different Y. You can only correspond to exactly one Y value. Okay, so that means the X, so here I got the same X value, same Q correspond to two different output. And that's what makes it not a function. Every different X can only correspond to one Y value. So you see the first one here, the Q, and the R is two different X value. Okay, as long as every different X value correspond to a Y value is a function. I cannot have the same X correspond to what? Different Y value. All right. So for a relation to be a function, every X corresponds to exactly one Y value. So you just can't have the same X value. Okay. For a relation to be a function, you just cannot have the same X value. All right. Go to different Y value. All right. I hope that kind of makes sense. So let's give this a try. Okay. This is very important. Can't have the same X value. So that's the first thing we check for a relation is to see if I have the same X value. All right. So here is a relation. 1, 2, 3, 4, 5 order pair together written in the set notation together. This is a relation. All right. Domain. Tell you what, I'm going to plot this real quick. 2, -3. To the right 2, down 3. I'm going to make this a little bit bigger. Maybe I can't. It's all right. 2, -3. To the right 2, down 3 is right here. 4, 2. 1, 2, 3, 4, up 2. This right here. -3, 3. There's a comma right here. -3, 3. 1, 2, 1, 2, 3, up 3. 1, 2, 3. It's kind of small. All right. -2, -1. -2, -1 is right here. And 4, -4. 1, 2, 3, 4. 1, 2, 3, 4. All right. So here are 5 points. Okay. There's no line connecting none of them. Okay. There's no line connecting all of them. It's just 5 separate points. So interval notation, as I mentioned in the review, is we can use it to describe domain and range. It's referring to from somewhere to somewhere, from -infinity all the way to infinity. That include everybody else in between. So there's no values between any given 2 points because this relation only consists of 5 points. So I cannot use the interval notation to describe my domain or the range. I have to use set notation. So write the domain, find a domain and write it as a set notation using brace. So domain is referring to X value. So all I'm going to do is write down all the X value, separate them by comma. All right, I wrote 4 twice. I don't need to write 4 twice. So I'm just going to stop at -2. All right, range is referring to the Y value. So I'm just going to put down all the Y value for range. So since there's no points in between, okay, these 5, so I put them in the set notation. Okay, so remember the biggest difference between set notation and interval notation is I use set notation if I only have these many answers. It's a finite number of answers. I can use a set notation. If I have infinite number of solutions, I can use interval notation to describe them. Okay, so all right, I plot the relation for you, just simply tell you that this is a relation. Is just a set of ordered pairs. We can write out the domain and the range as a set notation. Determine whether the relation is a function or not a function. Okay, is it a function? The answer is no, because earlier I just said for a relation to be a function, I cannot have the same X. This X, I got 4 twice. Okay, it does not correspond to exactly one y value. It actually corresponds to my same x actually correspond to two different y value here. Okay, it's almost like saying one butt cannot ride two horses. All right, one butt cannot ride two horses. That's basically what's going on here, if you want to think of it that way. All right, it got to be different x value correspond to one y value. So may I have all different kinds of x value, but all go into the same y value? Yes, you can. Okay, because this is different butts all riding the same horse. We're sharing the same horse, kind of like, right? The pony that we ride at the zoo. A lot of people don't sit on it. A lot of kids don't sit on it. And that is actually a function. Just cannot have the same x value. All right, so this relation is not a function. So I'll kind of double my question here. I'm going to just delete that one. I think in my handouts, I deleted that. All right, if not, we need to write down. Oh, you know what? Let me move this over here. All right, if the relation is not a function, then I need to identify the ordered pair as the reason. So the reason is 4, 2 and 4, -4. These two ordered pair is the reason why my relation is not a function. Okay, so quickly summarize what we talk about today. A relation is simply a set of ordered pairs. Okay, the first component is x value, or we call it domain. The second component is the y value, or we call them the range. All right. So domain is always labeled as x value. We can call them input, independent variable, or looking at a graphing perspective, it's about how wide the function is. Okay, thinking about two dimensions, x-axis and y-axis at the same time. How left does it go? How right does it go? Range is labeled as y value, output value, dependent variable, or how tall it is. Okay, how tall does my graph go, and how low is it coming from? Okay, and then we're talking about to be a function, for a relation to be a function, or for a graph to be a function, for an equation to be a function. I just cannot have the same x value. All right, it got to be different x value correspond to one y value. Okay, just cannot have the same one. All right, so that will conclude this video. Thank you for watching.